Hello everyone, this is the fourth video related to Higgs coupling. So here we will discuss various examples of intramolecular Higgs coupling, but I will suggest you to watch the previous videos related to Higgs coupling, especially the video where the introductory idea of intramolecular Higgs coupling I have discussed. Okay, so let's start. Here we have the first example of intramolecular Higgs reaction. So if we look at the structure, first of all we have to find out the reaction positions, that is where the CC coupling will actually take place. So in presence of this palladium catalyst, first this Ci bond, that is the carbon halogen bond, that will be broken and there will be formation of PDI. Now the CC double bond with which it will be coupled, that is actually positioned here. So if we are numbering here 1, 2, 3, 4, 5, 6, 7, then you can see that here coupling will be taking place at 1 and 6 positions. And if you look at the product, this is the newly generated bond. Let me do the numbering. 1, 2, 3, 4, 5, 6. That means now this is the 7, and if I put here 8, now the newly generated double bond after beta hydride, syn beta hydride elimination, that is at 7 and 8 position. So here this is the interesting point, that the CC bond doesn't end up in the original position means the 6, 7 position. Now it is ending up at 7, 8 position. Why? Because of the requirement of syn beta hydride elimination. So when finally the PD and H will be removed, then we need the hydrogen and PD to be in the same site, syn beta hydride elimination, and that is possible only at 8 position. That is the reason the CC bond doesn't end up at its original position. Next example here we'll see. Okay, so in this example this is 6 exocyclization, because the attack is here. That means the double bond is outside the newly generated ring. Fine. And here we are getting a quaternary center at this position. This is spider ring also. Next example, here we have this Ci. So first there will be PDI generation, and after that there will be CC coupling. So suppose this is 1, 2, 3, 4, 5, 6. So this is the connection point 1 and 6. And if I put here 7 and 8, after syn beta hydride elimination, the same logic will also be applicable here. Now this is shifted at 7 and 8. So the original positions, if we do the numbering, 1, 2, 3, 4, 5, 6. So originally it was at 6, 7 position, but now this is shifted because of this requirement. And this is also 6 exo, and here we are getting tertiary center generation. So this is after CC coupling, this is a tertiary center generated. In example 3, first we will find out the carbon halogen. So this is the carbon halogen. There will be formation of PDI first, and I will put the numbering here 1, 2, 3, 4, 5 and 6. So here 1 and 6, that will be the connection, that is the CC bond generation. So here you can see tertiary center is generated. And okay, and if I write here 7 and 8, so initially the CC double bond is at 6, 7 position, but it will end up at 7, 8 position, as you can see here. And if I do the numbering here, it will be 1, 2, 3, 4, 5, 6. So this is a 6 exocyclization. And why it is ending up at 7, 8, that we have already discussed in the previous examples. In the next example, here we have this carbon bromine bond that we can easily recognize. And if we put here numbering 1, 2, 3, 4, 5, 6, 7. So here 5 exocyclization will take place. That means 1 and 5, this will be the connection point. And if I do the numbering in the product, then it will be 1, 2, 3, 4, 5, 6, 7. So you can see now the original CC double bond position is at 6, 5. But now it is ending under 6, 7 position. So again we have to give the same logic. Here we are getting this type of bicyclic structure. And this is 5 exocyclization, because we are getting 5 member ring. And as the connection is like this, so the double bond, it is outside the newly generated ring. That is why it is 5 exocyclization. Then we have, this is very interesting, because first you will see here intramolecular reaction to take place, and after that there will be intermolecular, because if you look at the structure of the left hand side molecule, here we do not have double bond but we have a triple bond where Higgs coupling is possible. So this is our CI. So first there will be formation of PDI 1, 2, 3, 4, 5, 6. So before it is reacting with the other substrate, which is the alkene also, it can react within itself. So that is why first we will get the intramolecular Higgs coupling. And after that, here 1 and 5 position, that means this is the connection point. So we will get a 5-member ring. And this is 1, 2, 3, 4, 5. Now this is our 6th position. And then at 6th position we have methyl also. But PDI will be connected here. Now this will react further with this CO2Me attached to this alkene. That means this substrate. So suppose if it is A, it is B. Now A already it is reacting. It has already reacted within itself, and now it is reacting with B. So what will be the product here? So see here, this full moiety, if we consider it as R, as if it is I, P, D, R. Now this R, that will be now inserted here. So the molecule will be CO2Me touched to the double bond, and as you can see, this is our R. So in the product side, that molecule you are seeing here, this is basically the R group. So this is very interesting. First we are getting intermolecular reaction, and then it is intermolecular reaction, that is the reaction with B. Now in this case, here high functional group tolerance we can see. This is basically one of the step at the very late stage in multi-step synthesis of a very large complex molecule. So if you look at the substrate here, this is already having very sensitive groups. There are some sensitive rings, protecting groups, everything is present here. But even if the Higgs coupling, all these functional groups, they are still intact, right? So what the reaction is actually happening, this is the carbon-iodine bond. So first there will be formation of PDI, and 1, 2, 3, 4, 5, 6. So at 1 and 6, this is the reaction. So this is basically exo reaction. We are getting 6-member ring generated here. So in this reaction we can see basically this example is a very ideal example of high functional group tolerance. So this is, you can say, one of the utility of Higgs coupling reaction, that under this reaction condition all the other part of the molecule that is intact. In this case, here we have a 6-member ring, right? Now suppose this part, if I am writing as R, this is containing the CC double bond, and this part, that is the pH along with this bromine attached to it, suppose this is R prime. Now this R and R prime, they are both in equatorial position. But if I flip the ring, now what will happen? After flipping, this will be something like this. And the R group is now axial. R prime is also axial. So here we have these hydrogens, you can see these are axial in the previous structure, but now they will be equatorial. So why these two come at axial position, though it is very strained? Because if it is not coming close to each other, that is R and R prime, which is actually the two part of the intermolecular Higgs reaction. This is our alkene, this side, and here we have the CBr part, that is the halogen. So the arene and alkene, they must both be in energetically unfavorable axial position so that they can come close to each other, and ultimately there will be formation of bond. So if I am putting numbering here, it will be 1, 2, 3, 4, 5 and 6. So you can see these are the positions where it is connected, and we are getting a 6-member ring. And in the product also you can see these two bonds, that is these two bonds. Now the connection is here, they are axial. So they are coming in the, that is just for the sake of the reaction to take place. The double bond and CBr, they must come close to each other. That is why this arene containing the Br and the alkene, that is the R prime and this is the R, they must be in energetically unfavorable axial position. And what is the driving force here? Because if they are not coming close to each other, the Higgs coupling is not possible. So this is the newly generated CC bond. So these are the different examples for intramolecular Heck reactions. In the next video, I'll discuss the asymmetric version and the tandem reaction that is also possible in case of intramolecular Heck reaction. Thank you for watching.